Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, breaking math. Go to zencaster.com/pricing and use my code breakingmath, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your. People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencaster.com/pricing and use my code breakingmath, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story.
Neuroscience is a topic that in many ways is in its infancy. The tools that are being used in this field are constantly being honed and reevaluated as our understanding of the brain and mind increase. And it's no surprise. The brain is responsible for the way we interact with the world, and the idea that ideas hone themselves is not new to anyone who possesses a mind. But how can the tools that we use to study the brain and the mind be linked? How do the mind and the brain encode one another? And what does Bayes have to do with this? All this and more on this episode of Breaking Math. Episode 53, Big Brain Time. I'm Sophia.
And I'm Gabriel.
And welcome to Breaking Math.
I will mention that we are recording this both for the Breaking Math podcast as well as for my YouTube show, the Touring Rabbit Holes podcast. So kind of a double show, a 2-in-1. And we are delighted to be interviewing a researcher from, I'm sorry, how do you say it? It's the Center for Human Neuroimaging, is that correct?
Yeah, it's the Wellcome Center for Human Neuroimaging at University College London.
Beautiful. Thank you so much. I am delighted today that we are interviewing a Dr. Peter Zeidman. Am I saying that correctly, sir? Awesome. So I am very, very active on Twitter, and I very frequently will talk about a math topic that we're researching for our show, and very often it has something to do with human consciousness, often inspired by Gödel, Escher, Bach. And I was very happy that one of the outreach folks from your research organization contacted me and suggested this interview. So I'm very happy about that.
And,
so
I think the first question that we should start with is, who are you and what do you do?
So my name is Peter Zeidman, as you introduced me, and I am a neuroscientist. So I develop technology for investigating networks in the human brain and how those networks change when we perform different kinds of tasks. So when, for example, when we remember events from the past. So I use that technology that I developed to investigate memory and imagination and how they link to visual perception. So how we kind of live in the present, how we remember the past and imagine the future.
You and I have talked a little bit about email, about your specialty in memory and also in imagination. And we talked a little bit about some recent science fiction. You had suggested the movie Memento. Full disclosure, I didn't see it yet. I meant to watch it before this interview, but life is crazy sometimes. But there's been many examples of science fiction where it talks about memory and imagination. And I think it's fun to bring it up, about who gets it right and what we can learn from it. Tell us a little bit about Memento. And why you like that movie?
Why did you suggest that? And how do the concepts involved? How might they relate to your work?
So there's different kinds, and I'm so aware that I'm starting sentences with "so." People really hate it when I do that. So I try not to do that again for the whole rest of the podcast. There are different kinds of memory, and what we know is that different kinds of memory involve different parts of the brain to different extents. And the kind of memory I'm really interested in is the kind of memory that lets you close your eyes and vividly imagine something, either in your past or in the present or in the future. That kind of memory, what's called episodic memory, your ability to kind of replay episodes in your mind's eye, that kind of memory is associated with a particular part of the brain called the hippocampus. And every neuroscientist has to have their favorite bit of the brain, and I love the hippocampus. And when you get damage to it, you get a particular kind of memory loss, which is the kind of memory loss you see in the movie Memento. And the character in that movie has difficulty in taking on new memories, what's called anterior grade amnesia. So he can remember things for a few seconds, minutes, but then as soon as he walks out of the room, he's forgotten everything that happened before, and it's turned into a plot where he has to. But I won't give too much away. The notion that there are particular parts of the brain that allow us to encode a kind of like a model or a representation of the world, and if those bits of brain are damaged, you get this profound loss. It turns out not only of our ability to visualize things from our past, but also to imagine the future. That's why I like that movie. Of all the memory-related movies, that's probably the most scientifically legit.
So you bring up the future. I did a little reading into the Bayesian neurology stuff, and it mentions quite a bit about the relationship between surprise and free energy. Is that part of the research that you do?
Sure. So, those are really big topics. And so that's what you're kind of talking about there is the relationship between information theory that I know Gabriel's very keen on, and how we think the brain works. So maybe it'd be useful just to kind of talk about some of the big ideas at the moment in how the brain works, because that then speaks very closely to the mathematics that goes with it, which is related to the probability and information theory. I guess one important unifying idea that is particularly important in a lot of different computational accounts for the brain today is that the brain is like a simulation engine. So the brain is constantly simulating. If the world was in this particular state, what would I expect to perceive? So if it were the case that there was a tiger hiding behind my bookshelf on the other side of the room, what patterns of light would I expect would be falling on my retina? What rustling sounds would be arriving at my ears? So that's the idea that the brain is constantly trying to predict what's going to happen next. If those predictions are right, then the brain doesn't have to do anything. If the prediction matches the sensory information, then the brain doesn't have to expend much energy. But if the prediction's wrong, so if something is surprising, if there's a mismatch between the prediction and the data, then the brain has to do work to kind of update its understanding of the world. So understanding how that kind of predictive engine is implemented in the brain, what are the computations it performs, and what's the actual wiring, what's the circuitry that lets that happen, that's key to modern computational neuroscience.
And so you mentioned the thing about if your expectations don't match reality, then the brain, it seems like almost like grinds. It has like a kind of like a reconfiguration process, and it seems like you're saying that drives the learning process, but is it just the learning process, or is it all aspects of neurology in the way in your findings and in the literature?
Yes, I mean, this idea of predictive coding is actually very, it's a really nice set of theories, or a really nice framework, because it can explain an awful lot of what the brain does. Not only memory as a separate process, but how we see, so perception, and how we move, actually, and how we take actions. The brain is really complicated, and just trying to work out how to ask the right questions about its organizing principles is a challenge. There's quite a nice way of thinking about it that came from a British neuroscientist and computer scientist called David Marr. And he had this idea of 3 levels of analysis. So kind of at the top level, you've got what the brain does, like the kind of computational account. What are the computations that the brain performs? And then at the level below that, you've got the kind of the algorithmic level. So what algorithms does the brain implement through its connections to make that happen? And then at the base level, you've got what's the physical implementation. So a brain doesn't have transistors like a physical computer, but it has a particular wiring, a particular circuitry. And kind of neuroscientists will focus probably on those different levels. And what's really interesting and useful is how those levels interact.
Yeah, I was just going to say, there seems to be quite a bit of overlap.
Absolutely, yeah. So, I mean, if you're asking, like, what's the role of surprise? So the role of surprise, we can understand it at kind of like the computational level. So if I was working in machine learning, doing data mining, I might use artificial neural networks, and they use these ideas from neuroscience to learn by minimizing the difference between the predicted and the actual data. So that's kind of at the algorithmic level. You can then come down to the circuitry level and say, now we know what computations the brain must be performing, what could we predict to see in the wiring? And that can actually tell you a lot about or help us to explain how the brain is wired. So for example, if the brain was performing this kind of prediction and prediction errors, we'd expect to see different kinds of connections. Connections going one way that carry the predictions, connections going other way that carry the prediction errors. And indeed, that is what you see. You see these different, what are called laminae, connections going in different ways. So your question is a massive one. What's the role of surprise? And it's a really important one. And basically, bringing it back to memory, when something occurs that we didn't predict, that's when we now need to update our memory, or in other words, update our model of the world.
Oh man, this is fascinating stuff. This is absolutely fascinating. I mentioned earlier that my obsession is Shannon's information theory. I mean, that we've done multiple episodes on Shannon's information theory itself, but the fascination with cognitive processes are that, once you understand Shannon's information theory, although we don't have transistors in our brain, it is understood that that whatever happens in our brain, it is a communication system, and it must follow the laws of physics, and it must follow Shannon's information theory. So for that reason, I'm still very, very curious about it. Reading on the website for your institute, there's a lot of discussion on hierarchies. And one of the things that I'm very curious about with our sensory, with our brain, is sensory processing, and how that deals not only with memory, but with the process of cognition itself. I mean, how many senses we have, how our brain takes in all of the information, even fundamentally down to bits and bytes, and then how are the hierarchies set up? What takes precedence?
Yeah, because I remember one thing that Gabriel's talking about, out of many, is we talked about this episode about how the amount of information that the neurons on the surface of the retina receive is much greater than the amount of information going through the optic nerve, and it's just very strange, all these different things, and that even seems to be greater than the amount of information that we could fundamentally process consciously. But so I have a question in that vein, and a little bit of a two-part question. A lot of people report when they're driving or when they're at the supermarket that they imagine crashing their car. Is that, and I noticed, and there's other phenomena like that seem to be related to things that you were talking about with expectation and predicting the future. Like I've heard of this thing called the fridge door effect, where you look for a bottle of ketchup and you point to everything and it's not ketchup, and you skip the ketchup because you're used to it not being ketchup. In light of all that, what are the role of studying phenomena in your field, and have you done any research on mental situations like OCD?
That's a big question.
Yeah, so there's a lot there. So absolutely. So I think maybe it would just be good to talk about then. So Gabriel raised this idea of hierarchies. Yeah. And then you're asking really interesting questions about how they relate to everyday life and how hierarchical messaging may go wrong in certain psychiatric or neurological disorders. So maybe it would be worth just explaining a little bit what we mean by a hierarchy. Because in neuroscience, we're often looking for kind of broad brush, unifying ideas that can explain a lot about the brain and try and simplify it down to some simple concepts. And one very powerful concept is the notion of hierarchies. So the idea here, as you said, is that we have got all this incredibly noisy information coming into our senses. I mean, just how noisy that information is quite amazing. And I think the example you gave there with the retina is a really nice one, because it'd be like the clear area of our vision, our foveal vision, where we can have really high resolution. It's really small, that area. It's about, if you were to hold your thumb out, then your clear vision is about double the width of your thumbnail. What you perceive is a high definition world around you. And that trick that the brain is performing kind of gives away some of what's going on here, because essentially what it has to do constantly is to infer the causes of sensation. So you've got all this noisy information. It's not enough to interpret what's going on in the world. The brain has to model or infer what the causes of those sensations were. So then that model then that I keep saying that the brain is creating has to be implemented in some way. And what you find is in the world, there are statistical independencies between certain things. In plain language, that means that certain things don't rely on each other. For example, what something is doesn't depend on where it is. So it would make sense then, if you were making a computer model or a neural model of the world, you could quite happily have separate bits of brain for representing what something is and where something is, because those things are distinguishable in the world. And so indeed, that's exactly what you see in the brain. You see that separation of streams of processing for what and where. And it turns out it's hierarchical. So what that means is at the very bottom level of the hierarchy, you've got, and maybe you covered this when you did a previous thing on the retina you mentioned. Very bottom of the hierarchy, you've got neurons that might encode a spot of light. Higher in the hierarchy, you've got neurons that might encode lines and shapes. Above that, faces. Above that, the concept of grandma. So you're kind of going right the way from the sensory level right up to the abstract level, and that's what a hierarchy is in the brain.
It's interesting that you bring up the concept of the grandmother neuron. It seemed like you were bringing it up indirectly. Do you want to talk about how maybe your research is and is not that? Because what I got the impression of is it seems like you're looking at the general structure and flow of neurons rather than individual sort of thing. Like it seems like you're looking at almost like neurons as like some kind of weird like mushy crystal.
So I think, the idea of the grandmother neuron is often brought up as a criticism of a way of thinking, to say could there be a neuron in your brain that represents grandma or Jennifer Aniston, and therefore if you were to lose that neuron, you'd lose that concept. It's not exactly true, because what we know is that any representation of information depends on overlapping neurons. So you'll have some neurons that activate. Maybe this is actually a good place just to introduce a separation of two different concepts of brain organization. One is functional segregation. So it is true that to a certain extent, different parts of the brain do different things. So there will be a part of the brain that responds to faces, part of the brain called the fusiform face area. If you don't have that, you can't see faces anymore. You get a condition called prosopagnosia. But there's a complementary concept, which is functional integration, which is that there's no part of the brain for any one task. There isn't a love gland, and there isn't a making a shopping list gland, and there isn't a moving your hand gland. Rather, all of these cognitive functions rely on overlapping neural networks. So going back to the grandmother idea, there will be cells that come into a particular configuration electrically and chemically to encode grandmother. But those same cells will be involved in representing other stimuli when they're in a different functional configuration. So that would be an idea of how information might be represented at each level of this hierarchy. The key thing about the hierarchy then is that messages get passed between the levels. So the idea is that from those from a high level, you've got predictions that come down the hierarchy. So a very high level region like the cells encoding grandma will say that if grandma is in front of me, this is what the face that I would expect to see. And in the face area, I would be able to compare the face that's being observed to what was being predicted. And if they mismatch, if they cannot explain what is seen, then prediction error signals are sent back up to the hierarchy to say, that wasn't grandma. So the idea is you've constantly, at every single level of the hierarchy, got descending predictions and ascending prediction errors. You asked a really good question about psychiatric and neurological conditions. One detail of this hierarchy is that the signals are not all treated equally. So signals are weighted by how important they are. Mathematically, this is referred to as precision or inverse variance. So the more confident a signal, you can think of it as being the louder that signal will be. So those prediction errors that go back up the hierarchy will be weighted by how big the prediction error is. It's called precision weighting. So that means that through this weighting of signals, we can either put more emphasis on our prior beliefs, the things that we already know, or we can put more emphasis on the data that we're experiencing. So an example would be vision is a pretty good sense. So if my vision disagrees with my sense of balance, I'm probably going to believe the vision more. And a concrete example of that is when you're sitting on a train and the train going the other way starts moving. And now you kind of got a feeling like you're moving. You know that feeling? It's like an illusionary feeling that you're moving because you can see the train going by. And because you've got two different senses in conflict. Ultimately, you're probably going to believe the vision more than your sense of balance and kind of get that illusion happening.
I do notice with the example that you just gave, though, I noticed that on like when that's happened to me, sometimes I think that I'm moving at first, but it switches often to the second thing. Like, is it anything like burning your hand on a pan where part of your brain reacts before the rest of it has caught up?
Yeah, I mean, so that this idea of a hierarchy goes all the way down to your hands, for example. So you've got these kind of loops of, we haven't actually talked about movement and action, so it gets a little bit away from memory. But you've got those loops going all the way down, including by your spine. So that's why you can actually move your hand away from something hot quicker than your brain can process it. But illusions are really fun because illusions highlight what happens when you get a conflict between two different kinds of information.
We actually did an example of mathematical illusions on this show. We had a whole episode on paradoxes. And I remember reading some neurological reports, and I know that you've written some stuff about, I think is how fMRIs can be a little bit misleading, like blood flows stuff. But I do know that I read something about like the response to beauty being possible to a mathematical formula like e to the I pi minus 1 equals 0. I know they showed a bunch of mathematicians that, and it had a greater response. And I guess that's also tied into the question of, in this hierarchy, can levels move or can levels be represented as other things at higher levels, not just check each other? Like, how does that work?
Right. So I think, yes. So to a certain extent, that hierarchy is going to be hardwired. So to a certain extent, we all have similarities in our hierarchies. And that's why, if we do a neuroscience experiment based, I work with human subjects. So if I take a sample of 30 people for an experiment, I can be reasonably sure that a lot of the gross organizing principles of that hierarchy will be the same for them as they are for the wider population, similar for research with animal models. But then there'll be individual differences as well. And as I say, learning is all about updating the connections, the synapses in that hierarchy. I think a key idea here is the relationship then between that hierarchy and ideas of mathematics, and particularly the idea of Bayesian inference. I don't know, have you covered Bayesian stuff in any of your previous...
We've touched on it. We've never touched on any mechanisms behind Bayesian inference. I mean, we could just tell the audience what Bayes' theorem is real quick. Bayes' theorem is if you... Actually, that would take a whole other thing.
Yeah, so we have an upcoming episode on Bayes' theory. Bayes' theorem.
Sure, but I think that just the basic take-home concept is enough here, which is that we have some beliefs about the world. We then get some data, some sensory information, and then to some extent, our new belief will reflect the data. But what's critical is that our new belief is a trade-off between our prior beliefs and the data. So if the data is really, really good, in other words, really, really precise, to use a mathematical language, then I'm going to be really influenced by the data and not so influenced by my prior beliefs. Reciprocally, if my prior beliefs are really, really confident, then I'm going to be much more influenced by my prior beliefs than the data. That's really relevant to these hierarchies in the brain, because the hierarchy in the brain is trying to do inference. In other words, it's trying to it's using these prediction and prediction error signals to infer the causes of sensations. Those signals are weighted and weighted by confidence, as I said. So a sense that is more precise, for example, will have a greater impact than a sense that is less precise. A consequence of that is that you can cast any kind of psychiatric or neurological disorder as a misspecification of priors. In other words, if someone's prior beliefs are wrong or they're overly precise, so people put too much emphasis on their prior beliefs or too little, then they'll over or underestimate how important sensations are. And to give a concrete example of that, imagine you saw a face in the clouds when you were looking up at the sky. Now, you have a strong prior belief that faces do not happen to live in clouds. So however compelling that data is, your prior beliefs are strong enough that you would ignore that. However, somebody with a disorder that gave them what's sometimes referred to as aberrant precision, in other words, too much confidence about their prior beliefs, may have signals coming from parts of the brain representing those beliefs that are too strong. And they will believe, they will overestimate the data and underestimate their prior beliefs. So getting that constant trade-off between your memories, in other words, your prior beliefs in Bayesian language, and the data, and how much to weigh each of those is a really important way of thinking about psychiatric illness. And there's a whole field of study looking at that, what's called computational psychiatry.
Wow. Goodness, that's a thick field there. There's so much going on there. I'm thinking about like strong beliefs, and I'm also, so Sophie and I judge speech and debate, and suddenly I'm thinking about like what it takes to get someone to reevaluate their beliefs and how that works at a neurological level.
And I mean, I know that in these United States that me and Gabriel are from, a lot of people are having horrible problems with their prior beliefs, like influencing all kinds of stuff. I mean, I've heard of people dying of COVID who, until their last breath in the hospital, will insist that they're not dying of COVID. Are there external factors, stress, any weird neurological stuff that can influence how much somebody is influenced by their own prior beliefs? And can that be, are these processes reversible?
It's a really fascinating area. It's not my area of research, but there is a whole field of neuroscience called, or field of psychology called metacognition. So metacognition is your ability to introspect on your own thoughts and confidence. And there's a lot of work going on to investigate what is common across people that have unusually high precision in their beliefs. And you can think of people who are overly confident in their beliefs, who may be perfectly healthy. In other words, this isn't something medical, but they just happen to be people who have very, very strong beliefs and therefore may disregard evidence. Or reciprocally, people who have too little confidence in their own beliefs and so overweight evidence and change their minds too easily. So the whole field of metacognition, I think, is an absolutely fascinating one. Wow. It just reflects the fact that we need not only to be able to model the external environment, but also to model our own thoughts.
I have a question. Have you had a finding that changed the way that you live your life?
That's a very good question. No, I don't think so. I think the whole being trained in the whole scientific process is quite useful because it helps you to have a system of, it makes you a very grumpy person who's going to ultimately question everything. The Latin motto of the Royal Society in London, which is the British Science Academy, is take no one's word for it in Latin. So scientific training does give you a certain immunization against taking people's word for it on scientific claims without a certain degree of scrutiny. That's probably quite healthy. Might also make you quite annoying at dinner parties.
Oh my God.
Yes. But so I think probably it's the way of thinking rather than any specific.
Yeah. Just on that question by itself, like in America, we are a very, very, very religious country. I'm sure you guys know that, across the pond there. But a lot of my family is very religious, and a common question is, what reinforces, say, religious beliefs, or what reinforces, skepticism, and, how the brain does belief at all. I say does belief. I realize how absurd that sounds. I think for me, when I was much younger, I realized I could force myself to take the emotion out of it and to not weigh my beliefs or weigh my understanding based on anything emotional whatsoever, good, bad, or otherwise. So... yeah, that's.
I do have a question though. It seems like emotions. Where do emotion? Because I know that one of the things that you all study over there is emotion, correct? One of the several facets of. Because I have it here that y'all study action, decision making, emotion, hearing, language, memory, navigation, seeing, etc.
Yeah, I don't personally study emotions. In fact, I go out of my way to make the experimental design and the experimental stimuli I use as unemotional as possible.
Can you tell us about a recent experiment that you've been involved with? Because I think that might be interesting to hear about.
Yeah, so I think the study of emotion is absolutely fascinating, but it's maybe tangential to kind of my interest. So I'm interested in the very fundamental processes in the brain that allow you to encode a situation. So, for example, if you just went into a new room that you've never seen before, and then later to bring that back into your mind's eye. Now, clearly, emotion is going to have a role in that because you're going to have, for example, a stronger memory, probably if something emotionally salient were to occur. But actually, I'm just kind of at the level before that, which is just asking, what's the very basic circuitry that allow that to happen? So, to give an example of a recent experiment, I was in a collaboration with a researcher at the UCL Institute in Nijmegen in the Netherlands, a colleague, Nadine Dijkstra. And it was a really nice experiment looking at the relationship between imagination and perception of objects. So they had to either imagine or perceive them. And we did some neural modeling on that data. The data was acquired using functional magnetic resonance imaging. So that's a technology that allows us to get an indirect measure of how hard the brain is working at each point in the brain. It's an indirect measure because it goes via blood flow, or the amount of blood oxygen, rather. So when a bit of your brain is working harder, it needs some more oxygen. So that gives us an indirect measure. And essentially, that measure is just a wavy line. So it is a line on a graph for every point in the head that just says how active was that bit of the head. But as neuroscientists who want to understand imagination and perception, wavy lines are not interesting. What we want to know about is the underlying neural circuitry. So that's where the mathematics comes in, because now we have to use mathematical models to say, if the brain was wired up in a particular way, this is the wavy line, the neuroimaging, magnetic resonance imaging signal I'd expect to measure. And once you've got that model that says, if the brain was wired up in this way, this is what I expect to measure, you can then run that model in reverse. So you start with the measurements that you've taken from someone's brain, you fit the model to the data using Bayesian techniques, and infer the underlying neural circuitry. And what we found, what Nadina found, the first author on that paper, is that you get this top-down versus bottom-up bias in the signaling. When you're imagining the stimulus, imagining the object, you get more top-down activity, and when you're perceiving it, you get more bottom-up activity. And maybe that also highlights the really weird symmetry we have in neuroscience between what the neuroscientist does and what the brain does. Because And neuroscientists have got all this information that's quite hard to make out. It's wavy lines, it's people's breathing, it's people's heartbeat. And we have to try and infer the causes of that data. Like, what was the neural circuitry that caused that data to come about? And that's a kind of a similar process that the brain has to perform when it's got all this noisy sensory data, and it's trying to test hypotheses about what was the causes of those sensations. And that's why you get the same kind of mathematics used, both as an explanation for how the brain works and as tools that we use to investigate the brain.
When you were talking about that kind of stuff, it reminded me of one time. I can't remember. One time it was like I bumped into a table, and then something else far away, like maybe 20 feet away, broke at the same time, and my brain immediately thought that they were related, and then it deciphered it. And is that the kind of thing that the kind of phenomena that you would study?
So are you thinking of something called the binding problem? And as a computer scientist, you might be better place to talk about that than me. Is that what you're thinking of there?
Oh, no, I just was wondering about the neural circuitry behind that, because I thought that I broke something 20 feet away. Then I realized, wait, that's silly. I can't influence things via telepathy. I must have just hit the table and somebody else must have bumped it.
I think that's a really cool example, and it brings together a few different ideas. The first one, which I thought you might be referring to, is a general problem of cognition, which is called the binding problem, which is if you have different things happening relatively close together in time, how do you know if they're parts of the same event or if they're different events? And it's the same thing with agency, right? So if something happens close in time to me doing something, how do I infer if I caused that thing out in the world or if it was just a coincidence? And that's a big problem in artificial intelligence and also in neuroscience. And it's a really cool problem, a really cool question. So an explanation for how the brain might do that when you bumped into your table is that it immediately, when you hear that sound, which you didn't expect, so that sound was a surprise. So you've now got these prediction error signals flying about in your hierarchy in your brain, and the brain is kind of trying to come up with an explanation. And maybe it tries two different hypotheses. One hypothesis is that you caused that by hitting the table, even though it's far away, and the other hypothesis is that it's a coincidence. So then you can ask, and this comes back to your earlier question about something called free energy, and your question, Gabriel, about information theory. You can then ask, how do I decide which of those two explanations is better? So which of two models or explanations for data is the better model? That's a problem the brain has to solve, and it's a problem that the scientist has to solve when comparing models of data in any field of science.
Wow.
Mathematics of this comes down to statistics, and specifically Bayesian statistics and probability. So the notion here is that you want to assess what's the probability of the data given explanation 1 relative to the probability of the data given explanation 2. The probability of the data given the explanation is a quantity called the marginal likelihood in probability. It's also called the model evidence. And it's a trade-off between two different quantities, which we call accuracy and complexity. So it's the accuracy minus the complexity. So mathematically, you can write it down, you can break it into those two terms. Accuracy is how well your model explains the data. So it's a correlation between what you predict and what you actually experience. Complexity is how complex that model has to be. How many parameters does it have to use in order to explain the data? And the definition of a good model statistically is how well is that trade-off achieved. So a really good model is highly accurate and not very complex. The bigger that trade-off, the better the model. So the brain is having to do that assessment. And that idea of complexity comes back to information theory, because in terms of mathematics, that's measured in bits. In a particular implementation of predictive coding, or Bayesian brain ideas called the free energy theorem. That complexity is the difference between your prior beliefs and your beliefs after seeing the data. So if my beliefs had to move really far away from what I believed before in order to explain that sound that you heard, that's a really high complexity cost. So that's going to be a very expensive model in terms of complexity. I realize this is sounding a little bit complicated because this whole field is linking together physiology, mathematics, probability, statistics, information theory. But I guess the take-home message from this part of it is your brain may be like a little scientist, trying to compare the evidence for different hypotheses, always trying to make them as accurate as possible and as
So it's not lost on me that the brain itself is doing exactly what you guys are doing. And it's almost this like meta recursive function where you guys are making a model of the brain, but your own brains are making a model of the world around you.
Yeah, those are going to be one of my questions at the end was, does it freak you out that you're a brain studying brains? But
you are brain studying brains. Totally. Anything you would like to say in the time remaining about your interests, whether it be memory or things like mental illnesses and our understanding of it, or things like photographic memory or any of that sort? I'd like to give the rest of the time to you and to what you'd like to talk about.
So, I mean, the focus of my research is looking at how memory changes as we get older. So I'm currently using all the technologies we've been talking about to look at what happens in the earliest stages of Alzheimer's disease.
Wow.
So kind of the application of this is not only cognitive neuroscience, which is fascinating in its own right and speaks to some very deep ideas of who we are. There's also clinical translation, because ultimately we want to be able to understand why do we have very subtle changes in memory performance, for example, in potentially the years leading up to a diagnosis of Alzheimer's. If we can better understand that, then we've got an opportunity potentially to intervene in these conditions at an early stage. I think there's exciting future work, both on the cognitive neuroscience side of memory, to use some of these mathematical ideas, join them together with ideas from psychology, which is done neuropsychology, from which we've done a huge amount about memory, and put those together. I think a whole separate thing, we could have done a whole separate podcast on it, is clinical application of neuroscience and asking what are the kind of important questions that neuroscience could contribute to in terms of understanding what goes wrong when people get sick. But obviously there could be at least, 5, 6, 7 podcasts on that topic.
Yeah. When you had mentioned, and I'll be quick here. Sure. In grad school, I took an elective class that was all about nanoparticles. What was absolutely fascinating is we were tasked with coming up with creative uses of nanoparticles. And we had a student in our class who was a chemist PhD student, and she almost single-handedly wrote a proposal for treating Lewy body dementia, which I think is very similar to Alzheimer's, specifically with magnetic nanoparticles that could cross the blood-brain barrier, and they would be attached to an antibody that links up with the plaque, both Alzheimer's and Lewy body dementia, and somehow she would use pulses to generate heat that theoretically, in her little plan, it would break up the plaque, and the Lewy bodies as a proposed treatment. She was she got her undergrad from MIT. She was exceedingly competent, but it was brilliant. And I mean, that would be a physical treatment, and I realize that's probably a separate topic. I only bring that up because I'm sure you're on the forefront of, trying to understand this disease and treatments for it and things like that. That got me initially interested in it. So
it's so interesting. And I say we use magnetic resonance imaging just to image the brain, to scan it. But as your former classmate, you can use these magnetic fields to move particles around. I've not heard of any kind of clinical application, but scientifically, I think it's very exciting. The other thing that's kind of on the horizon is using focused ultrasound. So ultrasound, again, you think of it as an imaging tool, but you can actually use it as an intervention. And the idea here is you could actually get you could get drugs in little globules into the bloodstream, and then only at the places where the focused ultrasound kind of pounds those little bits of drug, does the drug get released, meaning you could release drugs into specific locations of the brain.
That should be really interesting for research, I imagine.
Yeah, very, very good for research. It could replace current, or at least supplement current technologies like optogenetics in a really straightforward way. So this focused ultrasound thing, I think, is going to be a really big thing over the next few years.
Awesome.
Yeah, and last thing is, do y'all have any plans for any kind of nanoparticles or anything to help see what neurochemicals are in which positions of the brain, or does that not factor as much into your research, the individual neurochemicals?
It's a really good question. So actually seeing neurochemicals. So the way the technology I use is MRI. MRI can and is increasingly being used in extremely clever ways to be able to detect the presence and levels of specific elements. So, for example, you can measure the level of iron in particular parts of the brain. And there's a whole field called quantitative MRI. That means that you can actually get numbers that have units, i.e. that have an actual meaning, and therefore could be used, for example, diagnostically. There's a whole different technology, a much older technology actually, but it's still very active and being developed, which is PET, positron emission technology.
Oh, yeah.
And PET has the ability, so with PET, you create agents that bind particular chemicals in the body. And increasingly, there are new compounds being developed for PET that could, for example, bind on specific pathologies you see in Alzheimer's disease. So there is a lot of exciting work being done with PET, what are called ligands that will bind on particular clinically relevant substances. And that's very exciting too. But unfortunately, I haven't got one of those to play with.
Well, let's hope you do sometime. Just kidding.
Yeah.
But thank you so much for coming on the podcast, the show, and again, your place of research is UCL.
Let me pull. I've got the website right here. Yeah, it is. It just says UCL, the Center of Human Neuroimaging. I believe that's the way it's called.
Wellcome Center for Human Neuroimaging. That's right. Yeah.
Awesome. Okay. Excellent. Well, yeah, I think we are at about time, but thank you so much. Absolute pleasure. Anything involving human cognition and mathematical models, we are obsessed with on this show. So maybe we'll have you back again sometime, you or any of your colleagues who want to come on. Tell them we'd love to have them.
Much appreciated. It's been a lot of fun.
In the United States and Britain, and London, actually. Or sorry.
No, the United Kingdom.
United Kingdom as a whole. Oh, yeah. Wow.
Because it turns out the United Kingdom, London, England, Britain are all.
I know. Sorry, Britain.
Summer concerts, pool parties, chill nights under the stars. We're stocking up our closet so you're ready to look your best for all of it. At Plato's Closet in West Ashley and North Charleston, we're buying all things summer. So bring in your tees, tote bags, sandals, sunglasses, and more. We pay cash on the spot for gently loved name brand looks. Plato's Closet is the go-to destination for trend-forward teens and young adults who support local and shop sustainable. Visit Plato's Closet today. Plato's Closet, located in West Ashley on Sam Rittenberg Boulevard and North Charleston on Rivers Avenue.